What are rational numbers? Well, rational numbers are numbers that can be represented as fractions. For example, a whole number, like say 7, well, that's 7 over 1. You can represent it as a fraction. You can represent it as a ratio of two integers. Now, if you want to express one of these fractions as a decimal, you divide the numerator by the denominator, which may or may not require a calculator. All rational numbers, they can be written as fractions, so ratios between two whole numbers, but also well, if you write them as a decimal, even if they are infinitely long, they repeat themselves. Irrational numbers are decimals without end that do not repeat themselves, such as pi. Pi is the ratio of the circumference to the diameter of a circle. It is an irrational number. It does not repeat itself. 3/4 can be written as a decimal. In this case, it's written as a finite decimal, so it has a finite number of places. 3/4 is 0.75 when written as a decimal. Negative 0.16 written as a fraction, well, that's equal to negative 16 over 100. In other words, you can cancel out a 4 from each, and you end up with equals negative 4 over 25. Now 8.2, if you write this as a mixed number, you start with, yes, okay, we can totally recognize the 0.2 is just 1 in 5, but because it's in a decimal format, it starts with 8 and 2 over 10, which is equal to 8 and 1 over 5. So let's write these fractions or mixed numbers as decimals. 2 over 5, that's equal to 0.4, because 1/5 is 0.2. 2 and 16 over 25. Oh, 16 over 25. How do we convert this to out of 100? Well, we multiply top and bottom by 4. So in other words, times 4 over 4. So that's equal to 2.64. Well, what about negative 2/3? As a decimal, we know that 2/3 is a repeating decimal. It's 0.6, a bunch of sixes, on to infinity. So, negative 2/3 is negative 0.6, repeating. Now, in some conventions, you use a dot if it's a single digit and a bar only when it's multiple digits repeating. But, well, a bar is also okay for a single digit, so we'll go with that. Okay, negative 4 and 3 over 11. So let's say we don't know the rules for dividing by 11. 3 divided by 11, oh, it's 0.272727, and so on. So this would be negative 4.27 repeating. Alright, let's write each of these decimals as a fraction or mixed number in simplest form. 0.8, well, we would start with, say, 8 over 10, right? Well, no, here we can just recognize it directly as, hey, this is 4 over 5. Like if you've done enough fraction to decimal conversion problems, you will recognize the common fractions that have relatively small denominators. Negative 0.15, well, let's start with negative 15 over 100. Well, that's negative 3 over 20. 0.111, and so on. What happens when you multiply by 9? You end up with 0.9 repeating, which, by the way, is mathematically proven to be equal to 1. Yes! 0.9 an infinite number of 9s is mathematically equal to 1. Really. Like, this is being proven. So, this is equal to 1/9. The length of the repeating unit is 1 digit. So you can multiply by a single 9 and see what happens. You start with the denominator being a single 9. Here, the repeating unit is also 1 digit. So you can also go with denominator equals 9. So, what do you think happens when the repeating unit is, say, 2 digits? Well, if it's 2 digits, you can use a denominator of 99. If the repeating unit is, say, 4 digits, 0. ABCD, or perhaps 0. something something something, and then ABCD repeating, this part you go with out of 9999, and if you have some more, say, zeros in front, you would just add a few zeros at the end here to space it out as needed. But in this case, if it's just 0. ABCD, you don't need anything here. If it's 5 digits repeating, start with 5 9s. If it's 6 digits repeating, you start with 6 9s, and so on. Now suppose we are comparing and ordering rational numbers. So if you've got to compare rational numbers, so things that can be expressed as fractions, you can either convert them to fractions with the same denominator, or write the numbers as decimals, or if they already have the same numerator, you can compare the denominators and go, this number is being divided by a larger denominator, which would mean that it's got a smaller magnitude if it's being divided by a larger magnitude denominator compared to the same number divided by a smaller magnitude denominator, which we'll see a little later. So let's say we replace the brackets here to make this true. Well, 4/5 is 8 over 10, which is, of course, larger than 7 over 10. Therefore, 4/5 is larger than 7/10. Okay. Order these rational numbers from least to greatest. Well, -3 1/3 is equal to -3.3 repeating, and -3 2/5 is equal to -3.4. Okay, from least to greatest, you gotta go from -3.4 up to -3.3 repeating, -3.25 with the 5 being repeating. By the way, if somebody gives you a repeating decimal like this with just a dot 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 at the end, that means that the last digit is what is being repeated. Otherwise, they would have to use a bar to denote which digits are being repeated. So writing it like this is perfectly normal. And the greatest would be -3.25. It's the least negative. So this, we kind of have to note that it is the order from least to greatest. Given that we had to write this line here, you can probably figure out why a lot of the time when ordering from least to greatest, people just put number, less than, next number, less than, next number, less than, next number. Yeah, it's a bit less writing. That's why people do that. Now let's do some exercises. We gotta fill in the brackets. I mean, I know it says replace the brackets, but they're big enough to fill in. So 5/6 versus 2/3. Well, 2/3 is 4/6. And 5/6 is clearly bigger than 4/6. Therefore, 5/6 is bigger than 2/3. 1/9 and 1/8. Well, 1 cut into 9 parts is going to be smaller than 1 cut into 8 parts. Well, each part is going to be smaller. Okay, 2.6 and 2 5/8. Well, 2 5/8 is 5/8 is 0.625. So compared to 2.6, yeah, that's bigger. So like this. Negative 4.58 and 4.58. Well, 4.58 is bigger than negative 4.58. All positive numbers are bigger than all negative numbers. Order each set of rational numbers from least to greatest. Well, the least here, 1/4 is 0.25, 2/3 is 0.6 repeating. So 0.1 is the least, is smaller than 1/4, which is smaller than 0.5, which is smaller than 2/3, 2/3. Okay. Here, 1.9 versus 2 point anything is gonna be smaller. So 1 and 9/10. And then 2 and 4/7. What is 2.4? 2.4 is 2 and 4/10. So 4/7, so 4 divided by 7, is clearly going to be bigger than 4 divided by 10. And since 4/10 is bigger than 0.13, 2.13 goes here, and then 2.4, and then 2 and 4/7. Okay. Negative 2 1/4, negative 2.28, negative 2.7, and negative. So this is negative 2.8. This is negative 2.25. Okay, so in order from, we want it from least to greatest, right? Yes. So from least to greatest, we got to go from most negative to least negative. That means negative 2.8 is smaller than negative 2.7, is smaller than negative 2.28, which is smaller than negative 2.25. Okay then, 4 2/3, well that's 4.6 repeating. Yeah, 4 5/6, 5/6 is bigger than 2/3. Okay then, but it's still going to be smaller than 5 point something. So 4.6 is smaller than 4 2/3, which is smaller than 4 5/6, which is smaller than 5.3. Multiplying fractions. Well, you multiply the numerators and you multiply the denominators after converting into improper fractions if you need to, and accounting for the number of negative symbols which may or may not cancel each other out, if there are any present at all, which is not the case in this question. 4/5 times 7/10 is equal to, oh, we want it in simplest form? That means that we should cancel out common factors between the numerators and denominators before we actually multiply. This way we can avoid having any common factors that we need to cancel out afterward. 2 times 7 on top, so that's 14, and 5 times 5 on the bottom, so that's 25. Okay, find negative 2 1/3 times 3 3/5 That's equal to negative 2 times 3 is 6 plus 1, 7 over 3 times. The dot product is perhaps not the most convenient for my writing utensil, so I'll use the x. 3 times 5 is 15. So 18 over 5. Now we can cancel the 3, and we end up with negative 42 over 5, which is equal to negative 8.4, or 8 and 2 over 5. Because it says simplest form, not decimal. So, multiply, write in simplest form. 2/3 times 3/5. Well, you can cancel out the 3's, which leaves you with 2 over 5. 4/7 times 2 over 4. Well, you can cancel out the 4's, which leaves you with 2 over 7. Negative 1/2 times 7 over 9. Well, there's nothing here you can cancel, so you just multiply the denominators for the new denominator and the numerators for the new numerator. And because there's only one negative symbol, you keep it. It doesn't cancel out. 7 over 18. And here, 2 and 2/5 times 1 over 6. You have 2 times 5 is 10, plus 2 is 12 over 5, times 1 over 6. So you end up with the 6 canceling with the 12, and you end up with 2 over 5. See, this is much easier to end up with a simplest form answer compared to multiplying and then factoring. So, negative 3 and 1/3, well, that's negative 10 over 3 times 3 over 2. So the 3's cancel, and then the 2 cancels with the 10 to give us a 5, so negative 5. 3 and 3 over 7. 3 times 7 is 21, plus 3 is 24, over 7, times 2 times 8 is 16, plus 5, 21 over 8. So 7 cancels with the 21 to give us a 3, 8 cancels with the 24 to give us, well, a 3 there, and 3 times 3 is 9. Now, negative 1 and 7/8 times negative 2 and 2/5. That is going to be negative 8 plus 7 is 15 over 8 times 2 times 5 is 10. 10 plus 2 is 12, right? Yeah, what about the negative symbol? Keep the negative symbol. That's important business. So 12 over 5. There are two negative symbols here that are being multiplied together. They will cancel each other out, and therefore the result is positive. So, what can we factor out here? Well, we can get a 3 up here. The 8 becomes a 2, and the 12 becomes a 3. So, 9 over 2. 9 over 2, technically this is in simplest form, but usually we mean as a mixed fraction instead of an improper fraction. And so negative 1 3/4, that's negative 7 over 4, times 2 times 5 is 10, so 11 over 5. There's nothing here we can factor out, so we're stuck with negative 77 over 20. So that's negative 3 and 17 over 20. 2 and 2/3. Well, that's going to be 8/3 times 2 and 3/7. 2 times 7 is 14, plus 3 is 17/7. There's nothing here to cancel, so we're stuck with, on the denominator, 3 times 7, which is 21. 8 times 17. Well, we know that 8 times 15 is 120. And then plus 2 times 8, so plus 16, yeah. 136/21. 126 is 6 times 21. So, 136 is 6, and then 10/21. So, if you're dividing fractions, well, if you have two numbers whose product is 1, they are multiplicative inverses, or usually just called reciprocals of each other. So write the multiplicative inverse of -2 3/4. Well, this is equal to -2 times 4 is 8, plus 3 is 11/4. So reciprocal is -4/11. Yeah, you just flip the numerator and denominator. If there's a negative sign, you leave it there, because two negatives multiply to positive. Hence, the product is 1. They are multiplicative inverses of each other. To divide by a fraction or mixed number, multiply by its multiplicative inverse or reciprocal. So find 3/8 divided by 6/7. Write it in the simplest form. Well, this is equal to 3/8 times 7/6. That cancels a little bit. So we end up with 7/16. Now, let's write the multiplicative inverse of each of these. Well, 3/5, we go to 5/3 for the reciprocal. -1/6, -6/1, or just 6. 2 3/4, that's equal to 11/4. And the reciprocal would be 4/11. 7 1/4, that's equal to 29/4. And if we take the reciprocal of this, we get 4/29. Now let's say we divide here, and we write these in the simplest terms. Well, 1/3 divided by 1/6, that's equal to 1/3 times 6/1. Well, you cancel that, and equals 2. So, 2/5 divided by 4/7 equals 2/5 times 7/4. Well, that cancels. 7/10. -6/11 divided by -4. Well, -6/11 divided by -4 is equal to multiplied by -1/4. And the 6 would cancel out to a 3, and the 4 would cancel out to a 2. Which means we're going to be left at 3/22. Now 5 divided by 2 1/3. Well, we got 5. Oh, by the way, if you need another step here, that's like divided by 2 times 3 plus 1 over 3 or whatever. If you need it, then do so. There is no shame in taking one more step. There is, however, a problem when you get something wrong. So yeah, just because I'm keeping the steps to a relative minimum doesn't mean you need to. 3 over, and 2 times 3 is 6, plus 1, that's 7, so we're left with 15 over 7, which is going to be 2 and 1/7. Let's say we want to add and subtract like fractions. Well, once we have the same denominator, fractions are considered like fractions. They are like each other. They are of the same type, same kind. And we can add the numerators, or subtract, as the case may be, and write the sum or difference over the same denominator. Like, say, 1/5 plus -4 over 5. This is 1 plus -4 over 5. In other words, -3 over 5. Or you can write the negative symbol in front of the thing for -3/5. Now for subtraction, we got, in this case, -4 minus 7 over 9. Which means -11 over 9. So -1 and 2/9. To add or subtract mixed fractions, you start by writing them like as improper fractions, and then you add or subtract said improper fractions. So here, 2 and 3 over 7. What's that? 2 times 7 is 14, plus 3, 17 over 7, plus 6 times 7 is 42, plus 5, 47 over 7. So, 17 plus 47. That's what? 13 plus 4 plus 47. 13 plus 47 is 60. So, 64 over 7, which is equal to 7 times 9 is 63. So, 9 and 1/7. Okay, let's add or subtract these and write them in simplest form. 4 over 7 plus 2 over 7 is equal to 4 plus 2, which is 6, over 7. 5 over 9 plus -1 over 9 is equal to 5 minus 1 over 9. So 4 over 9. Now 1/6 plus -5 over 6. That's 1 minus 5 over 6. So -4 over 6, which is equal to -2 over 3. 5 over 11 minus -4 over 11 is just going to be 5 plus 4 over 11. So 9 over 11. I mean, yeah, you could write 5 minus -4, but if you open the brackets, these negative symbols multiply each other to oblivion. Okay, -4/5 minus 3 over 5 is equal to -4 minus 3, so -7 over 5. That's equal to -1 and 2/5. 2 and 1/4 plus 1 and 1/4 is equal to 3 and 2 over 4. That means 3 1/2. Okay, How about with these mixed fractions? Well, you can certainly convert them into improper fractions first. So 26 here. 3 times 7 is 21 plus 5. And 2 times 7 is 14. 14 plus 3 is 17. So 26 plus 17. What's that? Well, so that's 26 plus 14 plus 3. So that gives us 43 over 7. 6 times 7 is 42. And we got a 1/7 here. So what else could we do? Well, we could kind of make this step already have the denominator merged, which means 4 times 5 is 20, 23, minus 2 times 5 is 10, 14 over 5. That leaves us at 9 over 5, which is 1 4/5. What if the denominators are not the same? Well, then these are called unlike fractions. How can we add and subtract them? We make the denominators the same by using the least common denominator, so the smallest common multiple of the original denominators. And we also multiply the numerators appropriately so that we don't end up going from 2 over 5 to, say, 2 over 10 without explanation. No, if you want to go from 2 over 5 to something over 10, it has to be 4 over 10. Remember, guys, from back when we were converting equivalent fractions? Yeah. So then you add or subtract as with like fractions, because by then they are like fractions. So 3 over 5 plus 2 over 3. Well, 5 and 3 are prime numbers, so you just got to multiply the two. So this is over 15 now, and that would be, because 5 times 3 is 15, 3 times 3 would be 9 for the new numerator. Plus 10 over 15 for the new version of 2/3. Right, in simplest form, this is 19 over 15. So 1 4 over 15. Okay, what about this next example? -3 1/2 minus 1 5/6. Well, 2 happens to be a factor of 6. Therefore, our least common multiple for the denominators is going to be 6. So, this, if you need, you can go -7 over 2 and then convert to something over 6. What over 6? Oh, well, you multiply by 3 over 3, so it's going to be 21 over 6. And it's negative. You minus 11 over 6. Okay, then you're looking at -32 over 6. In other words, 16 over 3. So this is -5 1/3. All right, let's say we want to add or subtract here with a few exercises. 2/5 plus 3 over 10. Well, 5 is a factor of 10, so we can just convert it into over 10. 4 over 10 plus 3 over 10 is equal to 7 over 10. 5 over 9 and -1/6. Well, 9 and 6, that's a 3 by 3 and a 2 by 3. that means our lowest common multiple is going to be a 2 by 3 by 3, which means over 18 for the lowest common denominator. So we're looking at a 10 over 18 here, and then plus negative 3 over 18. So 10 minus 3 is 7 over 18. Now for negative 3 over 4 minus 5 over 6, we got a 2 by 2 and a 2 by 3, so the lowest common multiple is going to be, or in this case, lowest common denominator, 2 by 2 by 3, which means 12. How many 12s though? This is 9 over 12, and then minus 10 over 12. So negative 19 over 12. Negative 1 and 7 over 12. Now for out of 3 versus out of 9, well, it's pretty obvious that the lowest common denominator is going to be 9. So first, you can decide to do this. 5 over 3 plus 4 over 9. In this case, we busted open the bracket, and because it was a negative in front, all the signs inside flip. So this would give us, out of 9, 15 plus 4. So 19 out of 9. Which means 2 and 1/9. Negative 7 over 10 minus negative 1 over 2. Well, the lowest common denominator is going to be a 10. So negative 7 over 10 plus 5 over 10. So that's going to be negative 2 over 10. Or you can just go with negative 1/5. Now 3 and 3/4 minus 1 and 1/3. That's equal to 15 over 4 minus 4 over 3. So out of 12, that's going to be 45 minus 16. 45 minus 16. Well, that's 45 minus 15 minus 1. So 29 over 12. Which leaves us at 2 and 5/12. Now, for these next two, negative 1 and 1/5 minus 2 and 1/4. That's negative 6 over 5. Minus 9 over 4. Equals, out of 20, it's going to be negative 24 minus 45. Okay. So minus 24 minus 45, that means negative 24 plus 45. What's 25 plus 45, guys? Because that's pretty easy, right? That's 70. So this is going to be negative 69 over 20. Okay. That's negative 3 and 9 over 20. In simplest terms, if you consider simplest terms to include change to mixed fractions if possible. Like instead of improper fractions. So 3 and 3/5 minus 2 and 2/3, that's equal to how much over 5? 18 over 5 minus 2 times 3 is 6 plus 2 is 8 over 3. So you could also change this problem to say 1 and 3 over 5 minus 2 over 3. Like that's okay, because you would just be canceling out some of the whole numbers first. So this is out of 15. So 54 over 15 minus 5 times 8 is 40 over 15. And that's going to be 14 over 15. Solving equations with rational numbers. Well, with rational numbers, it still holds true that if you do the same thing to both sides of an equation, it's still going to be equal. Like, let's say, solve x minus 2.73 equals 1.31. Well, x is equal to 1.31 plus 2.73. Okay, that's going to leave us at 4.04. So, check your solution. Left side is equal to 4.04 minus 2.73. And in case you don't trust my mental math for whatever reason, or you don't trust your own mental math for whatever reason, when you're doing a problem, do use a calculator if you need to. However, for a subtraction that's like this, no, you don't need it. So it's equal to right side, therefore QED. There, answer has been checked. Solve, or, well, I mean, it says, technically means what's asked has been proven. Or shown, but whatever. So 4/5 y equals 2 over 3. Y is equal to 2 over 3 divided by 4 over 5. Or you can just go straight to this step, 2 over 3 times 5 over 4. Because you could say, oh, I multiplied both sides by 5 over 4, and on this side it canceled. The 2 and the 4 cancel. So we end up with a 5 over 2 times 3 is 6. Now check our solution. Left side is equal to 4 over 5 times 5 over 6. Which means that the 5's cancel and the 6 it becomes a 3, the 4 becomes a 2, which is equal to 2 over 3, which is equal to right side. Therefore, what's asked has been shown. Well, let's solve some equations, and then we'll check the solutions. So t plus 1.32 is equal to 3.48. That means t is equal to 3.48 minus 1.32. So, this comes out to 0.16 and 2 up here, 2.16. So, left side is equal to 2.16 plus 1.32, which is equal to 3.48. Oh, it's equal to right side. Wonderful. Therefore, what has been asked has been shown. Negative 8.07 equals r minus 4.48, while r is equal to negative 8.07 plus 4.48. R is equal to 4.48 minus 8.07. Negative 3.59. Okay, well, what is the right side here? The original right side. Well, let's sub this in and see if it works. Negative 3.59 minus 4.48. In other words, negative, bracket, 3.59 plus 4.48. Close the bracket. Okay, what happens? Oh, 0.52 and 0.48 would come out to be another whole number. So we have 0.07 left. And it's going to be negative 8.07, which is equal to the left side. Oh, wonderful. So what's been asked has been shown. Great. What about 3.2c is equal to 9.6? Well, c is equal to 9.6 divided by 3.2. Okay, so we divide both sides by 3.2 and we end up with c equals 3. Okay, then let's check if this is true. Left side is equal to 3.2 times 3, which is equal to 9.6. So it's equal to the right side. QED. Hurrah! Okay, what about if 3/5 of x is equal to 6? Well, you could go x equals 6 divided by 3 over 5, or you could just go 6 times 5 over 3 and be like, oh, I just multiplied both sides by 5 over 3. And on the left side, it canceled to give a coefficient of 1. Hurrah! Yeah, in other words, we would have saved a step easily without any fuss. So x is equal to 10, and our left side is 3 over 5 times 10. So this cancels to give a 2. This equals 6, which is, it's the right side. It's equal to the right side. Therefore, we've proven that our answer is correct. Okay, what about negative 2/3 is equal to 3 over 5t? Well, t is equal to negative 2/3 times 5 over 3. So negative 10 over 9, which is equal to negative 1 and 1/9. Okay then, let's say we test this. Okay, so the right side is equal to 3 over 5 times negative 10 over 9. Well, this cancels to give a 2, and this cancels to give a 3. Gasp! It's equal to negative 2/3, which is equal to the left side. So we proved that our answer is correct. Yeah, so if you do the same thing to both sides of an equation, the equation stays true. Unless, of course, you mess something up. In which case, yeah, no, you didn't do the same thing to both sides. Or maybe there was a typo in the equation itself that you were given. Well, who knows? These things happen sometimes. So, what you have here is a bunch of mixed fractions. You don't want there to be any issues when you're moving them around, so you might as well convert them to improper fractions before you make any adjustments. 1 3/4 is 7 over 4, which is equal to 3 times 8 is 24, plus 5 is 29 over 8. Well, this is going to be 29 over 8 times 4 over 7. Because, well, if you multiply this by 4 over 7, it cancels. So, this leads us to cancel this. And we get 29 over 14. Which means 2 and 1 over 14. Left side is equal to 1 3/4 times 2 and 1 over 14. So 7 over 4 times 29 over 14. And 7 times 29 is, 7 times 30 is 210. This is going to be 7 less, so 203. 4 times 14 is 56. And what happens when we consider what 3 times 56 is? 3 times 56 is 168. So 203 minus 168 is 35. So we get 3 and 35 over 56. 35 is 5 times 7. And 56 is 8 times 7. So it's equal to 3 and 5/8, which is equal to the right side. And thus, we've shown that this calculation, this answer for R, is correct. Obligatory problem solving section. Look for a pattern. You can look for a pattern to solve a problem as part of your typical problem solving strategy. 3 people board the subway train at the first stop, 5 people at the second stop, 7 at the third stop, and the pattern continues. And no one gets off the train. How many people are on the subway train when it reaches the 7th and final stop? No, this is not odd prime numbers. Okay, that's just trolling. This is just odd numbers. Occam's razor is with just the simplest explanation that accounts for all the variables is probably correct. Is the most likely. So, how many people are on the subway train when it reaches the 7th and final stop? Well, first, so this is the stops. And no one gets off the train, so boarders. The first stop, 3 people board. Second stop, 5 people board. Third stop, 7 people board. Fourth stop, 9 people. Fifth stop, 11 people. Sixth stop, 13th people. And 7th stop, 15 people board. So we're looking for total equals 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. Which means you're looking at 7 over 2 times 3 plus 15. Because they're symmetrically distributed around the middle number, you can always just go with the middle number times the number of terms, or you can go with pairs, in which case there's 7 over 2, or 3.5 pairs, and multiplied by the sum of each pair. So you're looking at 7 over 2 times 3 plus 15, so 18. In other words, 7 times 9. Or 63. So there are 63 people on the train. People are aboard. Now let's say we look for a pattern with these problems. In this case, a pattern could be just a fixed ratio, such as a muffin recipe calls for 2.5 cups of flour for every 2/3 cup of sugar. How many cups of flour should be used when 4 cups of sugar are used? So 2.5 to 2/3 is equal to x to 4. let X cups flour be used. Okay? So, this you can cross multiply. Because what this ratio means is that this is a bigger fraction. You can rewrite this as 2.5 over 2/3 is equal to x over 4. You can multiply the denominators across at each other, and you would get 2/3 x is equal to 2.5 times 4. So 10. And x would therefore, of course, be equal to 15. So 15 cups of flour should be used. Now let's say we have 256 people at a fundraiser, and half the people who remain leave every 5 minutes after the event is over. How long after the event ended did the last person leave? Time. Minutes. People. Well, at 0 minutes after the event's end, there were 256 people left. And at 5 minutes, you had 128 people left. At 10 minutes, you had 64 people left. Or you could just go as 256 is equal to 2 to the what power? It's equal to 2 to the 8th power. Because 1024 is 2 to the 10th. So 2 to the 8th power, and therefore to get to 2 to the 0th power, you need how many time frames? You need 8 time frames. And that means after 40 minutes there would be one person left, and then presumably at 45 minutes that person would leave. Of course, if you want to use a table, go ahead, I guess. 20, 16, 25, 8, 30, 4, 35, 2, 40, 1, and 45, presumably the last person left. Because I don't think half of the person would have left. Yeah, mathematically speaking, an infinite time after the event ended, the last person left. But realistically speaking, the last person left. The last person left at 45 minutes. If you have a bunch of repeated factors, you can write them using exponents, such as 5 sevens multiplied together is 7 to the 5th power. And if you have 3 p's and 2 q's multiplied together, that's p to the 3rd power. It shows up 3 times multiplied together. And q to the 2nd power, because there are 2 q's multiplied in. Any non-zero number to the 0th power is 1. And any non-zero number to the negative nth power is the multiplicative inverse of nth power. So in other words, x to the power of negative n is equal to 1 over x to the nth. Okay? So let's evaluate 6 squared. This is equal to 6 times 6, which is 36. And 5 to the negative third power, that's equal to 1 over 5 to the third power. And 5 to the third power is 25 times 5. So 125. 1 over 125. Now exercises. Write each expression using exponents. 8 times 8 times 8 times 8 times 8 is equal to 8 to the fifth power. You have 4 4s multiplied together, which is 4 to the fourth power. And if you have how many 5s? 1, 2, 3, 4, 5. So that's 5 to the fifth power. And how many 9s do you have? 1, 2, 3. Times 9 to the third power. And here, how many s's do you have? You have 1, 2, 3, 4 s's. So s to the fourth, and you have 2 w's, so w squared. Now, even if it was s squared, w to the fourth, you would still write the s first. Why? Because the convention is that you write the variables in alphabetical order within each term. Evaluate each expression. 13 squared. 13 times 13 is 169. 2 to the third times 3 squared is equal to 8 times 9, which is 72. 3 to the power of negative 4 is equal to 1 over 3 to the fourth. So that's 1 over 81. 3 to the fourth times 7 squared. Well, 3 to the fourth is also 9 squared, so that's 81 times 7 squared is 49. So 49 times 81, 3969. A number in scientific notation is written as a number between 1 and 10. It can be 1. So it's a times 10 to the nth power, where a is greater than or equal to 1, but strictly less than 10. It can't be 10, because otherwise you would just have, well, another exponent on the 10. So, you use the power of 10 to indicate the place of these numbers that you're multiplying it into. So 8.65 times 10 to the 7th power is 865. And, well, 8 is supposed to be followed by up to 7 zeros, but in this case we have a 6-5 taking up 2 of the places, so we just have 5 zeros left. Like here, this is 8 times 10 to the 7, and the 0.65 is this part here. Notice how this is 7 digits. And that 10 to the 7th power is going to have 7 zeros with a 1 at the front. 9.2 times 10 to the negative third power. Well, 10 to the negative first, 10 to the negative second, and 10 to the negative third is here. So this is 10 to the negative first, 10 to the negative second, and then 10 to the negative third is going to be 0.001, and then multiply by 9.2 for this. 76,250 in scientific notation is equal to 7.625 times 10 to the fourth. Because there are 4 digits after the first one. That the first non-zero digit. And, well, we write all the non-zero digits and any zeros that are in between them as the part that's being multiplied to the position indicator. Indication. I mean, that's the purpose of the 10 to the whatever's power that you multiply in. Write 0.00157 in the scientific notation. Well, that's 1.57 to the negative first, negative second, negative third. Okay. Times 10 to the negative third power. Scientific notation is good for very large and very small numbers. It's usually not so great for numbers that are, say, 5.3 times 10 to the first power. Dude, that's just 53. And 9.4 times 10 to the third power. That's 9,400, guys. 8.651 times 10 to the negative second power. Well, that's equal to 0.10 to the first and 10 to the second. Okay. 8,651. 6.7 times 10 to the negative 6. Oh, that's 10 to the negative first, negative second, negative third, fourth, fifth, and then the sixth. And you have the 6 and the 7 at 10 to the negative 6 for the 6. Because that's the ones digit of the thing you're multiplying in. Now you write each of these numbers in scientific notation. 5, 6, 4. There's quite a few of zeros. But we notice that this is an 8-digit number. So after the first digit, there are 7. Which means it's equal to 5.64, all the digits that actually contain useful information. And then you times 10 to the 7th to give it a position. In this case, that means that there's 7 digits after the first one. 7 digits which give you the position of the first one as the 8th digit. Okay, 0.752. That's 7.52 times 10 to the negative first. The 7 is at the 10 to the negative first position, so the 1/10. And then the 5 and the 2 come after. 0.0064, well, that's 6.4 times 10 to the negative third. The 6 is at the 10 to the negative third position. Here, well, the 5 is at 10 to the negative fourth. And it's 5.81 by 10 to the negative fourth. So yeah, scientific notation is a way to make numbers that are pretty long shorter to write. Or shorter to enter into, say, a computer. And less prone to making mistakes. What else can it be used to? It can also be used to express rounding. Like say, you have this number. Which digit is it rounded to? Has it been rounded to the nearest 1,000? The nearest 100,000? The nearest 10? The nearest 1? We don't know. But if you write it like this, aha, it's been rounded to the nearest, see which digit it is? Okay, it's been rounded to the nearest 100,000. It's been rounded to 3 significant digits. Whereas if you otherwise have a bunch of placeholder digits, what precision have we made the measurement to? We don't know. Yeah. So, that's it for this chapter, and we'll see each other again next chapter.